All right, this is Honors Algebra 2 Pre-Calculus. We're doing 5.6 in Algebra 2. This is the third video. We're doing complex conjugates and the division of complex numbers. So in order to simplify a fraction containing complex numbers, you often need to use what's called the conjugate of a complex number. So for example, the conjugate of 2 plus 5i is 2 minus 5i. The conjugate of 1 minus 3i is 1 plus 3i. So the conjugate of a complex number, sometimes called the complex conjugate, of a plus bi is a minus bi. You're literally just changing the sign on the imaginary term. And the way we denote the conjugate of a plus bi is a plus bi with a line over it. So what you're actually doing here, just to clarify, right? So the idea of a conjugate is what you're doing is you're creating a difference of squares. So that's what multiplying a plus bi times a minus bi does. So you're creating a difference of squares to remove the I terms. So I terms. So let me just show you how that works, right? So here's how it works. If I were to take a plus bi and multiply it by the conjugate of a plus bi, right, the complex conjugate, that's the same as a plus bi times a minus bi. Well, look what happens when I FOIL, right? I get a squared. Outer and inner are going to cancel. I'm going to get a negative abi and a positive abi. Well, those are going to sum to 0, right? That's what happens on a difference of squares. They sum to 0, and my back term is going to be a negative b squared times I squared, right? Well, that would be the end of it, except that it's imaginary numbers. So a squared minus b squared times a negative 1 is the same as a squared plus b squared. There are no i's. So what you've done by creating this difference of squares, by multiplying a plus bi times its conjugate, is you've gotten rid of the i's. So when we're simplifying a quotient with imaginary numbers, what we do is we multiply by a fraction equal to 1 using the conjugate of the denominator, and this is called rationalizing the denominator. So let's go ahead and walk through this. If I want to simplify 2 plus 5i over 2 minus 3i, the rule, what we mean when we say this, is no i's in the denominator. So you're allowed to have i's in the numerator, and the reason you're allowed to have i's in the numerator is you want your answer, right? You want your answer to look like a plus bi. Well, that i's in the numerator, that's totally fine. So here's what I'm going to do. I'm going to take this 2 plus 5i over 2 minus 3i, and I'm going to multiply it by the complex conjugate of the denominator. So I'm going to multiply by 2 plus 3i over 2 plus 3i. I have to multiply by something over itself because this entire fraction is a 1, right? I have to multiply by 1. So when I do that, when I FOIL the numerator, right, I'm going to get, so first, outer, inner, last, right? I'm going to get first is going to be 4. Outer is going to be plus a 6i. Inner is going to be a 10i, right, plus 10i. And last is going to be plus a 15i squared. In the denominator, what's going to happen is the i's are going to cancel, as we've already seen. My first is going to be 4, but my outer and inner are going to sum to 0 because they are a plus 6i and a minus 6i. That's not an accident. That's what's supposed to happen. If it doesn't happen, you multiplied wrong. And then I get a minus 9i squared. But remember, we know that my I squareds aren't really I squareds, they're negative 1s. So this is a 4 plus a 16i minus a 15 on top. And on the bottom, I have a 4 plus a 9. So what's going to happen is I'm going to get negative 11 plus 16i over 13. To write this in standard form, I need to split it into my real part and my imaginary part. So this is my a plus bi. All right, so I'm going to go ahead and let you try P7, which is the same idea. So again, we're going to write this in standard form. That involves rationalizing the denominator. So you can go ahead and pause me if you want. I'm going to walk through multiplying both the top and bottom of the fraction by the conjugate of the bottom, right? When I FOIL, I'm going to get 6 minus 3i minus 8i plus a 4i squared. On the bottom, I'm going to get 4 minus 2i plus 2i. Remember, this was the whole point of this thing, was to make this oi sum to 0 minus an I squared. Remember that my I squareds are not really I squareds. They're actually negative 1s. So I'm going to get that this is a 6 minus 11i minus a 4, right, because it's 4 times a negative 1. And on the bottom, I'm going to get a 4 plus a 1, because it's 4 minus a negative 1. So I get 2 minus 11i all over 5. My final answer will be split into the real part minus the imaginary part, or plus the imaginary part, but in this case it was minus. All right. So complex numbers can also be graphed. This is not a particularly useful skill. I'm just going to throw this out there right now. So if you graph a complex number in the plane, essentially the x-axis acts as your real axis, the y-axis acts as your imaginary axis. So if you were to plot a plus bi, you would plot it at the point a comma b. For example, 3, 2, right? So 3 plus 2i is plotted at 3 comma 2, because this is the real component and this is the imaginary component. The I is what makes it imaginary. It has 2 of those imaginary units. So you can see that's the example of how you graph these. The absolute value of a real number is its distance from 0 on a number line. Similarly, the absolute value of a complex number is the hypotenuse of this triangle. It's the distance from this point to the origin. So essentially, it's just Pythagorean theorem, right? So the absolute value of a plus bi is going to be the square root of a squared plus b squared, because this is a leg of the triangle and this is the other leg of the triangle. So if you were asked to find the absolute value of 3 plus 2i, it would be the square root of 9 plus 4, or the square root of 13, okay? So let's go ahead and keep moving forward. All right, you're asked to evaluate the absolute value of the absolute value of negative 2 minus 3i, and you're asked to sketch a diagram that shows these. So remember, my x-coordinate is going to be negative 2, right, on the x-axis, and my y-coordinate is going to be negative 3. So if I were to sketch this, and I'm going to do a terrible job, but we'll survive. This is the point, right? This is the point that represents negative 2 minus 3i, right? That's that point. And then, oh, I'm terrible at drawing. It's cool. All right. So this is a negative 3. This is a negative 2. This line, right, the hypotenuse, is that absolute value. So the absolute value of negative 2 minus 3i is going to be the square root of negative 2 squared plus negative 3 squared, which is going to be the square root of 13. All right. Again, I'm not going to make you do this a lot and ever. It's not a particularly useful skill. All right, so you're going to evaluate the absolute value of negative 3 plus 5i, and then you just sketch a diagram. So we can go ahead and do this first if you want. The absolute value of this thing is going to be the square root of a squared plus b squared, right? Which should be a square root of 34, right? If I draw this on a diagram, my x-coordinate is negative 3, my y-coordinate is 5, so it's going to look something like this. And again, it's technically not the x and y axis, it's the real and the imaginary axis, but you get the idea. They happen to take place on top of what we would call the x and y axis. So this is a negative 3, this is a 5, and then this hypotenuse is the absolute value of negative 3 plus 5i, which happens to be a root 34. All right, and that is it for our video.